Right now, a black hole is destroying something physics says cannot be destroyed. The rules say nothing truly disappears. Quantum mechanics demands it. Yet, black holes seem to erase everything that falls inside forever. This clash has haunted physicists for 50 years. We call it the information paradox, and it threatens everything we know about reality. You will journey through firewalls that burn at the edge of darkness, holograms that encode universes and wormholes connecting distant particles. If you enjoy mysteries that bend your mind, hit that like button. Prepare yourselves. We begin. A book burns. The pages curl and blacken. Smoke rises into the air. Everything scatters into ash and gas molecules. Physics says you could theoretically reverse this process. Every atom, every photon, every quantum state could be tracked backward in time. The information about those pages still exists, just scrambled across millions of particles. This principle is called unitarity. It states that information in our universe can never be truly destroyed, only transformed. Quantum mechanics stands on this foundation like a building on bedrock. Now imagine that burning book falls into a black hole instead. The gravity pulls it past the event horizon. The pages stretch and tear in the immense tidal forces. Eventually, everything crosses into darkness. From outside, the book disappears completely. No light escapes to tell us what happened to those words, those atoms, those quantum states. The black hole grows slightly larger, absorbing the mass. But where did the information go? What happened to the quantum states that described every particle in that book? For decades, physicists assumed the information simply sat inside, frozen at the singularity where all matter gets crushed to infinite density. That seemed reasonable. The information still existed, just trapped forever behind the event horizon. We could not access it, but it was there. The laws of quantum mechanics remained intact. Nobody worried too much about books or astronauts we could never retrieve from beyond that boundary. Then Stephen Hawking changed everything. In 1974, he published calculations that shook physics to its core. Black holes are not completely black. They radiate energy. Quantum effects near the event horizon create pairs of particles. One falls in, the other escapes. Over incredibly long time scales, this Hawking radiation causes black holes to evaporate. A black hole, the mass of our planet, would take longer than the current age of the universe to disappear, but eventually it would vanish completely. Here is the problem. Hawking radiation appears to be completely random thermal radiation. It carries no information about what fell into the black hole. When the black hole finally evaporates completely, all the information about everything that ever fell inside seems to be gone forever. The book, the astronaut, every quantum state erased from existence. This directly violates unitarity. It breaks the fundamental rules of quantum mechanics. You cannot have it both ways. Either information is destroyed, which means quantum mechanics is wrong, or information escapes somehow, which means our understanding of black holes is wrong. Both options are terrifying. Quantum mechanics has been tested billions of times and never failed. General relativity describes gravity with stunning precision. Yet they cannot both be right about black holes. This is the information paradox, and it has divided physicists into warring camps for half a century. What makes this worse is that we cannot simply ignore it. Black holes exist throughout the universe, millions of them. If they routinely break the laws of physics, then something fundamental about our understanding of reality is broken. The paradox is not just about black holes. It is about whether our most successful theories can coexist or whether one must be wrong. The solution, when we find it, will revolutionize physics. But which will fall? Quantum mechanics, general relativity, or both? We are about to explore every major attempt to solve this crisis. Stephen Hawking was not looking for a paradox. He was trying to understand what happens at the quantum level near a black hole's edge. Classical physics said nothing could escape a black hole. Quantum physics whispered something different. The event horizon, that invisible boundary where escape velocity equals light speed, is not smooth when you zoom into quantum scales. The vacuum itself is violent there. Empty space is never truly empty. Quantum mechanics tells us that particle pairs constantly pop into existence, then annihilate each other within a fraction of a second. An electron and its antimatter twin, a positron, flash into being, exist for an instant, then collide and vanish. This happens everywhere all the time. Near a black hole, something strange occurs. The intense gravity can separate these pairs before they recombine. Imagine a particle pair, materializing right at the event horizon. One partner falls across the boundary into the black hole. The other escapes outward into space. From far away, it looks like the black hole just emitted a particle. This is Hawking radiation. The escaping particles carry energy away from the black hole. Since energy and mass are equivalent through Einstein's famous equation, the black hole loses mass. Slowly, over eons, it shrinks. The temperature of this radiation is incredibly cold for large black holes. A black hole with the mass of our planet would have a temperature far below the cosmic microwave background that fills space. It would actually absorb more radiation from the universe than it emits. But smaller black holes are hotter. A black hole the mass of a mountain would glow white hot. One the mass of a car would explode like a nuclear bomb. Here is what troubled Hawking. The radiation seems completely random. When that particle escapes, it carries energy, but it appears to carry no information about what fell into the black hole. Whether you threw in a book, a computer, or a star, the radiation looks the same, just thermal noise. The radiation is determined only by the black hole's mass, charge, and spin. Nothing else matters. Over time, the black hole evaporates completely. First, it takes billions upon billions of years. Then, as it shrinks, the process accelerates. The smaller it gets, the hotter it becomes, radiating faster. In its final moments, a black hole releases a tremendous burst of energy as the last fragments of mass convert to radiation. Then nothing remains. The black hole is gone. All the information about everything that ever fell in supposedly gone with it. Every book, every atom, every quantum state that crossed the horizon erased. This cannot happen according to quantum mechanics. Information must be conserved. Yet Hawking's calculations were rigorous. They followed from combining quantum field theory with general relativity near the event horizon. The math was sound. Hawking himself initially believed information was truly destroyed. He argued that black holes were the one place in the universe where quantum mechanics failed. This position sparked intense debates. Physicists gathered at conferences and argued for hours. Some supported Hawking. Others insisted there had to be a way for information to escape, even if we could not yet see how. The stakes were enormous. If Hawking was right, we needed a new theory of quantum mechanics. If he was wrong, We needed a new understanding of black holes and gravity. Either way, a revolution in physics was coming. The question was which foundation would crack first. But proving either side seemed impossible. We cannot create black holes in laboratories. We cannot watch them evaporate. The smallest black holes we know about are still several times the mass of our planet. They will not evaporate for an incomprehensible span of time. How do you test a theory when the experiment takes longer than stars will shine? Two theories rule modern physics. General relativity describes the universe at its largest scales. Quantum mechanics governs the smallest. They are both stunningly successful. Relativity predicted black holes, gravitational waves, and the expansion of the universe. Every test confirms it. Quantum mechanics gave us transistors, lasers, and an explanation for why atoms do not collapse. It has never been wrong in a single experiment. Yet they speak different languages. General relativity sees spacetime as smooth and continuous, like an infinite rubber sheet that bends under mass. Roll a ball across this sheet and it follows a curved path, what we call gravity. The equations are deterministic. Give Einstein the precise state of the universe at one moment, and he can calculate its state at any other moment, past or future. Quantum mechanics sees reality as fundamentally uncertain. You cannot know both where a particle is and where it is going with perfect precision. The act of measurement itself affects the outcome. Particles exist in superposition, occupying many states at once until observed. The theory deals in probabilities, not certainties. It is built on the principle that information is never lost, just spread out in increasingly complex ways. These differences did not matter for decades. Relativity handled planets, stars, and galaxies. Quantum mechanics handled atoms, electrons, and light. Their domains barely overlapped. Physicists could use one theory on Monday and the other on Tuesday without worrying about contradictions. Both worked perfectly in their own realms. Black holes change that. They are massive enough that relativity governs their behavior, yet small enough that quantum effects cannot be ignored. At the event horizon, both theories must apply. This is where the clash becomes unavoidable. Relativity says spacetime should be smooth even at the horizon. For someone falling in, crossing the boundary should feel. Hawking radiation is random and carries no information. If you could somehow measure the radiation, you would find that it is random and carries no information. This is a consequence of the uncertainty principle, which states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. In other words, the more precisely you measure the radiation, the less precisely you can know the information it carries. This is a fundamental limit to what we can know about the universe, and it is a consequence of the uncertainty principle. Hawking radiation is random and carries no information. Then the information inside is destroyed when the black hole evaporates. But quantum mechanics forbids this. The theory would collapse if information could be destroyed. Every prediction, every calculation relies on this conservation principle. One theory demands smoothness at the horizon. The other demands information preservation. Pick one, and you violate the other. This is not a small technical problem. It is a war between the two pillars of modern physics. Entire careers have been spent defending one side or attacking the other. Some physicists tried to modify quantum mechanics to allow information destruction. They proposed that black holes were special exceptions, places where the normal rules did not apply. This felt like giving up. Quantum mechanics works everywhere. else we have tested it. Why would it suddenly fail at a black hole? Others tried to modify general relativity. Maybe space-time is not smooth at the horizon. Maybe something prevents information from truly falling in, or allows it to escape in ways we have not detected. But messing with general relativity is dangerous. Change one piece and you risk breaking predictions that have been confirmed by countless observations. The paradox forced physicists to confront an uncomfortable truth. Our two best theories are incomplete. They are spectacularly accurate approximations, but they cannot both be fundamental. Somewhere deeper lies a theory that unifies them, a quantum theory of gravity. The information paradox is a crack in the facade, showing us where our understanding breaks down. Solving it requires finding that deeper theory. We need to understand what happens to space-time at scales smaller than anything we can observe, where quantum effects and gravitational effects are equally strong. This is the Planck scale, where lengths are measured in units 100 billion times smaller than a proton. At this scale, space-time itself might not be smooth. It might be grainy, foamy, or made of something we cannot yet imagine. The black hole information paradox is not just about black holes. It is a signpost pointing toward the next revolution in physics. Whoever solves it will rewrite our understanding of space, time, and reality itself. Chapter 4. The Holographic Principle. In 1993, a physicist named Gerard Don Hooft proposed something outrageous. Maybe the three-dimensional universe we experience is actually a two-dimensional projection. Everything you see, every object, every person, every star, could be information encoded on a distant surface. Like a hologram, the 3D world emerges from 2D data. This idea sounds like science fiction. It came directly from thinking about black holes. The key insight involves entropy. In normal matter, entropy measures disorder, the number of possible arrangements of particles. The more particles you have, the more entropy. If you double the volume of a gas, you roughly double its entropy. Entropy scales with volume in 3 dimensions. Black holes do not follow this rule. A black hole's entropy depends on the surface area of its event horizon, not its volume. Jacob Bekenstein discovered this in the 1970s. The bigger the horizon, the more entropy the black hole can hold. But entropy measures information. If a black hole's information is proportional to its surface area, then somehow all the information about everything inside is encoded on the two-dimensional horizon. This seems impossible. Take a black hole and throw in a library. The books pass through the horizon and fall toward the center. They occupy three-dimensional space inside. How can all that information be encoded on a two-dimensional surface? Yet the math insists this is true. The area of the horizon increases exactly enough to account for the information in the books. And Hooft extended this reasoning. If black holes encode 3D information on 2D surfaces, maybe the entire universe does the same thing. Perhaps all the particles, forces, and fields filling three-dimensional space are actually projections from information stored on a distant boundary. We are living inside a hologram, though one far more sophisticated than any image on a credit card. Leonard Susskind embraced and expanded this idea. He argued that the holographic principle could resolve the information paradox. If information falling into a black hole is simultaneously encoded on the horizon, then it never truly disappears inside. When the black hole evaporates, that information can escape through the Hawking radiation because it was on the surface all along. This requires something deeply strange. An object falling into a black hole must exist in two places at once. From the perspective of someone watching from far away, the object's information gets smeared across the horizon, scrambled by quantum effects, but never destroyed. From the perspective of someone falling in with the object, it passes smoothly through the horizon and continues inward. Both descriptions are valid. Both are real. This duality appears to violate common sense. How can the same information exist in two places simultaneously? Susskind called this black hole complementarity. It depends on the fact that no single observer can see both versions. The outside observer can never cross the horizon to check if the information is also inside. The falling observer cannot send signals out to confirm the information is also on the surface. The speed of light prevents any contradiction from being directly observed. Critics attacked this immediately. It seemed like cheating. You cannot just say information is in two places because nobody can check both. That feels like a violation of physics, not a solution. Moreover, black hole complementarity created its own problems. If information is encoded on the horizon, what happens to an observer who falls through? According to general relativity, falling through an event horizon should feel normal. The horizon is not a physical barrier, just a mathematical boundary. You would not notice crossing it any more than you notice crossing the equator. But if information is encoded there, the horizon might not be empty. It might be a raging firewall of high-energy particles incinerating anything that tries to pass through. This firewall paradox, which we will explore shortly, emerged directly from taking the holographic principle seriously. The more physicists tried to save information conservation, the more they seemed forced to sacrifice the smoothness of spacetime. The paradox was mutating, spawning new forms, resisting every attempt at resolution. Yet the holographic principle continued to gain support. In string theory, physicists discovered mathematical examples of holographic dualities, relationships where a quantum theory in one dimension precisely describes gravity in a higher dimension. These were not vague analogies. They were exact mathematical correspondences. The hologram idea was not just speculation anymore. It was woven into the structure of candidate theories for quantum gravity. The universe as a hologram challenges our deepest intuitions about reality. If, and Hooft and Susskind are right, then depth is an illusion. The dimension we experience as extending forward and backward is emergent, projected from information that fundamentally exists on a surface. We are not living in three-dimensional space. We are living in a three-dimensional shadow. Chapter 5. The Firewall Paradox. In 2012, 4 physicists published a paper that reignited the information war. Ahmed Almhari, Donald Marf, Joseph Polchinski, and James Sully showed that saving information from black holes might require burning anyone who approaches one. Their argument came to be known as the firewall paradox, and it forced physicists to make an impossible choice. The reasoning starts with quantum entanglement. When particles interact, they can become entangled, linked in a way where measuring one instantly affects the other, even across vast distances. Einstein called this spooky action at a distance and hated it. But experiments confirm it happens. An entangled pair shares quantum information in a profound way. Now, consider Hawking radiation more carefully. The particles that escape from a black hole come from quantum pairs created at the horizon. One partner falls in, the other escapes. If the escaping particle is to carry information out of the black hole as the holographic principle demands, it must be entangled with particles inside. This entanglement is how information escapes. The radiation is not random after all. It is subtly correlated with what fell in, though the correlations are scrambled in extraordinarily complex ways. Here is where the problem arises. A quantum particle can only be maximally entangled with one other system at a time. This is called the monogamy of entanglement. You cannot have a particle entangled with two different systems simultaneously. Yet the firewall argument showed that the escaping Hawking radiation must be entangled with two systems at once. First, the escaping particle must be entangled with its partner that fell into the black hole. This entanglement is how the particle pairs are created in the first place. Without it, there is no Hawking radiation. Second, if information escapes, the escaping particle must also be entangled with all the radiation that has already left the black hole. This is necessary to preserve information. The correlations between early radiation and late radiation encode what fell in. Both entanglements are required. Both cannot exist. The monogamy of entanglement forbids it. Something has to give. The four physicists argued that the only way to break the entanglement between the escaping particle and its infalling partner is to make the horizon violent. A firewall of high-energy particles must incinerate the infalling particle immediately, severing the entanglement. This is catastrophic for general relativity. A firewall at the horizon means the horizon is not smooth. It means falling into a black hole would not be the gentle crossing predicted by Einstein's equations. You would burn to death at the boundary, cooked by intense radiation appearing from nowhere. An observer hovering just outside the horizon would not see the firewall. An observer falling through would encounter an inferno. Space-time itself would be observer-dependent in a way general relativity never imagined. Many physicists rejected this conclusion outright. The idea that space-time could be so dramatically different for different observers violated too many principles. Others embraced it as a proof that general relativity breaks down at the horizon. Still, others searched desperately for a way around the firewall argument, a hidden assumption that might be wrong. Some proposed that entanglement monogamy could be violated in subtle ways. Maybe a quantum state could be entangled with multiple systems if the entanglements were arranged correctly. These proposals required modifying quantum mechanics in strange ways. Others suggested the horizon itself might not be a sharp boundary, but rather a fuzzy region where classical spacetime breaks down. If there is no precise horizon, maybe there is no precise location for a firewall. Stephen Hawking, by this point, had changed his mind about information destruction. He now believed information must escape, though he could not explain exactly how. Faced with the firewall paradox, he proposed something radical. Maybe black holes do not have event horizons at all. Instead, they have apparent horizons, temporary boundaries that eventually release everything. Matter would not fall into a singularity, but rather get stuck near the surface, slowly radiating away. This would solve the paradox, but would also mean black holes, as we understand them, do not exist. Leonard Susskind and Juan Maldisa offered a different escape. They suggested that the entanglement between the escaping particle and the particle inside the black hole could be equivalent to a wormhole connecting them. If wormholes and entanglement are secretly the same thing, then the monogamy of entanglement might not apply in the expected way. This ER equals EPR proposal linking Einstein-Rosen bridges with Einstein-Podolsky. Rosen entanglement opened yet another strange door. The firewall paradox revealed how fragile our understanding truly is. Every attempt to preserve one principle seemed to shatter another. Information conservation clashed with smooth space-time. Quantum mechanics clashed with general relativity. No matter which direction physicists turned, contradictions emerged. The paradox was not just a puzzle anymore. It was a signal that something fundamental about our theories is wrong. What happens at the horizon of a black hole? Do you fall through smoothly or burn instantly? The answer might depend on whether information or space-time is more fundamental. One of them might be emergent, arising from something deeper. The firewall paradox is pushing physicists toward a radical possibility. Maybe space and time themselves are not fundamental. Maybe they emerge from the quantum information that underlies reality. Chapter 6. Entanglement and the EPR Paradox. In 1935, Einstein, Podolsky, and Rosen published a paper they believed proved quantum mechanics was incomplete. They described a thought experiment where two particles become entangled, then separate by vast distances. Measure one particle spin, and the other particle spin is instantly determined no matter how far apart they are. Einstein argued this was absurd. Information could not travel faster than light. Therefore, the particles must have predetermined properties all along. Quantum mechanics was missing something: hidden variables that determined outcomes in advance. Einstein was wrong, but in an interesting way. Experiments by John Bell in the 1960s and countless tests since then confirm entanglement is real. When you measure one particle of an entangled pair, the other particle's state truly does change instantaneously. Yet no information travels between them. You cannot use entanglement to send signals faster than light, because the measurement outcomes are random until you compare them. Only when you bring the measurement results together do you see the correlation. This weirdness is central to the black hole information paradox. If information escapes from black holes through Hawking radiation, then entanglement must somehow connect the radiation to what fell inside. The correlations are scrambled across thousands or millions of outgoing particles, making them nearly impossible to decode, but they must be there, or information would be lost forever. Imagine throwing an encyclopedia into a black hole. The information describing every page, every word, every arrangement of atoms is encoded in quantum states. As the black hole evaporates, that information must leak out through the Hawking radiation. Each particle carries a tiny fragment of the original information, entangled with earlier and later particles in a fantastically complex pattern. Reconstructing the encyclopedia would require collecting all the radiation and performing measurements that are far beyond any conceivable technology. This is why Hawking initially thought information was destroyed. Even if the information technically escapes, it is scrambled so thoroughly that it seems lost forever. The distinction between destroyed and irretrievably scrambled feels academic. Yet quantum mechanics insists the distinction matters. In principle, the information could be recovered. The universe does not care whether we have the technology or not. The firewall paradox exploits the EPR connection. The escaping Hawking particle must be entangled with its partner inside the black hole due to how the pair was created. This entanglement seems necessary for Hawking radiation to exist at all. But the escaping particle must also be entangled with previously emitted radiation to preserve information. Both entanglements cannot coexist according to the monogamy principle. Some physicists wondered if entanglement itself works differently near black holes. Maybe the extreme curvature of spacetime modifies quantum mechanics in subtle ways. These modifications would have to be incredibly precise, appearing only in the most extreme conditions while leaving all other quantum predictions untouched. Proposing such modifications felt like grasping at straws. But desperate times inspired desperate theories. Others explored whether the entanglement between Hawking radiation and the black hole interior might not need to be maximally strong. Perhaps weaker partial entanglements could carry enough information out without violating monogamy. These proposals required detailed calculations, tracking how information flows from inside the black hole to the outside through layer after layer of quantum correlations. The math became nightmarishly complex. Juan Maldacena and Leonard Susskind proposed that Einstein-Rosen bridges, better known as wormholes, might be the geometric manifestation of quantum entanglement. If two particles are entangled, they are connected by a microscopic wormhole through spacetime. This ER equals EPR conjecture suggests entanglement is not just a quantum correlation, but a physical connection through space. If true, the entanglement between the Hawking particle and its infalling partner would be a tiny wormhole connecting them. This reframes the entire paradox. The infalling partner does not simply fall toward the singularity. It remains connected to the escaping particle through a quantum wormhole. As the black hole evaporates, these connections might allow information to flow outward through paths we had not considered. The singularity might not be an endpoint, but rather a hub linking different parts of spacetime through quantum geometry. Testing these ideas seems hopeless. We cannot create black holes. We cannot measure correlations across event horizons. Yet, physicists have found proxies. Quantum computers can simulate the entanglement patterns that would appear in Hawking radiation. Tabletop experiments with analog black holes created in fluids or light can mimic some horizon effects. These tests cannot prove what happens in real black holes, but they can rule out some proposals and support others. Entanglement remains the key to solving the information paradox. It is the mechanism by which information might escape, the force that creates firewalls, the phenomenon that might be equivalent to space-time geometry itself. Understanding entanglement deeply enough to resolve these contradictions would be a triumph. It would show us how quantum mechanics and gravity fit together at their most fundamental level. Chapter 7. The Fuzzball Theory. String theory reimagines particles as tiny vibrating strings rather than point-like dots. Different vibration patterns produce different particles. An electron is one vibration, a quark another, a photon yet another. This elegant idea aims to unify all forces and particles into a single framework. When string theorists examined black holes through this lens, they found something unexpected. Black holes might not have singularities at all. In classical general relativity, the center of a black hole is a singularity, a point where density becomes infinite and equations break down. This signals where the theory fails, where quantum effects must take over. String theory suggests that instead of collapsing to a point, matter falling into a black hole gets tangled into a dense ball of strings and higher dimensional membranes. Samir Mata called this a fuzzball. The fuzzball has no event horizon in the traditional sense. The entire object is a quantum mess of vibrating strings with no clear boundary between inside and outside. From a distance, it still looks like a black hole. Light cannot escape from deep within the tangle. The gravitational pull is identical to what general relativity predicts. But zoom in close, and instead of a smooth horizon, you encounter a chaotic quantum structure. This solves the information paradox elegantly. There is no singularity to destroy information. The information that falls in gets encoded in the configuration of strings that make up the fuzzball. As the fuzzball radiates, the strings rearrange and information escapes through the radiation. No information is ever hidden behind an impenetrable horizon because there is no horizon. Everything is surface. Critics point out that this seems to conflict with general relativity. An observer falling toward a black hole should experience a smooth crossing of the horizon. Fuzzball theory suggests the horizon is not smooth at all, but rather a messy quantum surface. This creates a variant of the firewall problem. Would you burn when you hit the fuzzball surface, or would you pass through smoothly? Fuzzball advocates argue that the quantum structure is so fine-grained that individual observers would not notice the messiness. The strings are unimaginably small, far smaller than any particle we know. An observer falling in would interact with so many strings simultaneously that the experience would average out to smoothness. It is like diving into water. Water is made of discrete molecules, but you do not feel individual molecules. You feel a continuous fluid. Whether this argument works depends on details of string theory that are not yet fully understood. String theory exists in 10 or 11 dimensions, with extra dimensions curled up too small to see. How the fuzzball structure appears in those extra dimensions versus in our familiar 3 dimensions of space remains unclear. The mathematics becomes ferociously difficult when trying to describe realistic black holes, especially rotating one. Despite these challenges, fuzzball theory makes a striking claim. Black holes are not holes at all. They are objects, exotic quantum objects, unlike anything else in the universe, but objects nonetheless. This demystifies them in some ways while making them stranger in others. Instead of a one-way door to oblivion, a black hole becomes a quantum archive, storing information in the patterns of strings that compose it. Another string theory approach involves higher dimensional geometry. In some versions, black holes in our 4-dimensional space-time, 3 space dimensions plus time, are projections of objects in higher dimensions. These higher dimensional objects might have no singularities and no information paradox. The apparent paradox in our dimensions would be an artifact of viewing a higher dimensional structure from a limited perspective. Both fuzzball theory and higher dimensional approaches require accepting string theory. That is a big leap. String theory has elegance and mathematical beauty, but it has not yet made testable predictions that distinguish it from other theories. We cannot build particle accelerators powerful enough to probe the energies where string effects become important. Every test of string theory so far has been indirect, comparing its predictions for already known physics to see if it can reproduce what we observe. This frustrates many physicists. String theory has dominated theoretical physics for decades, consuming vast intellectual resources, yet it remains unproven. Alternative theories of quantum gravity, like loop quantum gravity, offer different solutions to the black hole paradox. The landscape of ideas is vast and without experimental data. Choosing between them feels premature. Still, fuzzball theory offers something valuable. It shows that the information paradox is not insurmountable. Modify our understanding of black hole structure at the quantum level and the paradox dissolves. Information is not destroyed because there is nowhere for it to disappear into. The horizon is not a boundary, but a transition zone. And the interior is not a separate region, but a dense tangle of quantum degrees of freedom. Whether this specific solution is correct, it proves that solutions can exist. Chapter 8. Loop Quantum Gravity. String theory is not the only attempt to quantize gravity. Loop quantum gravity takes a different approach, one that does not require extra dimensions or vibrating strings. It starts with general relativity and tries to make spacetime itself quantum mechanical instead of smooth, continuous geometry. Spacetime is built from discrete chunks woven together like a fabric. At the smallest scales, space comes in quant. The Planck length, about 100 quintillionth of a trillionth of a meter, sets the scale where quantum gravity effects dominate. Loop quantum gravity suggests that at this scale, space is grainy. You cannot divide it further. Area and volume come in minimum units. This discreteness prevents singularities from forming. When matter collapses, it cannot squeeze into an infinitely small point because there is a minimum size. Apply this to black holes, and something interesting happens. The crushing gravity near the singularity where classical equations break down is where quantum effects take over. Instead of infinite density, the collapsing matter reaches a maximum density and then bounces. The gravitational pressure cannot crush it further because there is no smaller space for it to occupy. This creates a Planck star at the center of the black hole, a tiny quantum object with enormous density, but not infinite density. The bounce takes time, but time is strange near black holes. From outside, the collapse appears frozen at the horizon due to gravitational time dilation. From inside, the bounce happens relatively quickly. The Planck star then expands, and eventually the black hole explodes from the inside out. This takes an enormously long time from the outside perspective, potentially longer than the current age of the universe. But it happens. If loop quantum gravity is correct, black holes are temporary. They are phases in the life cycle of matter. Stuff falls in, compresses to a Planck star, bounces, and eventually erupts back out. The information that fell in remains encoded in the quantum state of the Planck star throughout this process. It is never destroyed, just transformed and stored in the dense quantum geometry. This avoids the paradox entirely. There is no singularity to destroy information. The event horizon is still there, but it is not permanent. Give it enough time and the black hole will erupt, spewing everything back out. The trick is that this eruption happens on time scales far beyond what we can observe. From a practical standpoint, black holes still look eternal, but in principle they are not. Critics of loop quantum gravity question whether it can reproduce all the predictions of general relativity in the appropriate limits. The theory is still being developed, and some calculations are incomplete. Whether it can describe rotating black holes, which are the most common type in nature, remains an open question. The mathematics is extraordinarily difficult, even more so than string theory in some respects. Another criticism involves Hawking radiation. Loop quantum gravity explains what happens at the singularity, but it is less clear about how information escapes through Hawking radiation before the final explosion. If information only gets released at the end after the black hole evaporates almost completely, then the paradox still exists for most of the black hole's lifetime. The information would be trapped until the final moment. Recent work has explored whether loop quantum gravity effects modify the horizon itself, allowing information to leak out gradually. Quantum corrections to the geometry might create subtle pathways for information to escape throughout the evaporation process, not just at the end. These calculations are ongoing. The theory is young compared to string theory, and many details remain to be worked out. What loop quantum gravity offers is a different philosophy. Instead of adding new structures like strings or extra dimensions, it takes the geometry of spacetime seriously and quantizes it directly. Space and time become quantum variables, fluctuating and uncertain at the smallest scales. This discreteness is both a blessing and a challenge. It prevents singularities naturally, but it also makes calculations harder because the smooth mathematical tools of calculus break down. Reconciling loop quantum gravity with other aspects of physics like the standard model of particle physics is another hurdle. String theory naturally includes matter particles and forces. Loop quantum gravity focuses on spacetime geometry, and fitting matter into the framework requires additional steps. Combining them into a complete theory of everything remains an unfinished project. Despite these challenges, loop quantum gravity shows that multiple paths toward quantum gravity exist. The black hole information paradox might have multiple solutions depending on which approach to quantum gravity turns out correct. Or perhaps elements from different approaches will merge into a final theory that borrows from both. The fact that several independent frameworks suggest information is preserved strengthens the case that information must indeed escape somehow. Chapter 9. Black Hole Complementarity. Leonard Susskind proposed a radical solution called black hole complementarity. The idea is that two observers can see fundamentally different realities, and both descriptions are correct. This sounds like madness, but quantum mechanics already includes similar ideas. Before measurement, a particle exists in superposition. After measurement, it has a definite state. The reality depends on perspective. Black hole complementarity applies this to horizons. An observer far from a black hole sees infalling matter slow down, flatten, and spread across the horizon. From this distant perspective, nothing ever crosses the boundary. Instead, information gets scrambled and encoded on the horizon surface. Over time, this information radiates away through Hawking radiation. The observer sees no paradox. Information starts outside, gets encoded on the horizon, and eventually escapes. Meanwhile, an observer falling into the black hole experiences something completely different. They cross the horizon smoothly, feeling nothing special at the boundary. They continue falling toward the singularity, carrying all their information with them. From this perspective, the information goes inside and sits there, never escaping. No Hawking radiation appears to carry it away because the falling observer does not see significant radiation coming from the horizon. Both stories cannot be true simultaneously in any classical sense. Information cannot be in two places at once. Yet Susskind argued that quantum mechanics allows this because no single observer can verify both descriptions. The distant observer can never cross the horizon to check if information is also inside. The falling observer cannot send signals back out to confirm information is on the surface. Relativity guarantees these perspectives remain isolated. This is complementarity. Different observers have complementary descriptions that are individually complete but mutually incompatible. It is similar to wave-particle duality in quantum mechanics. Light behaves like a wave in some experiments and like a particle in others. Ask which it really is, and quantum mechanics says both descriptions are equally real depending on how you measure. Extend this idea to black holes, and you get complementarity between inside and outside. Critics immediately attacked this proposal. It seemed to violate the principle that reality is objective. Either information is inside or it is on the surface. Saying both just because nobody can check sounds like evasion. Moreover, complementarity seemed to work only if you accept some very non-intuitive assumptions about how information is encoded and how observers are defined. The firewall paradox emerged partly from trying to make complementarity rigorous. If information is encoded on the horizon and also falling inside, then the horizon cannot be empty. It must have structure. Push this logic far enough and you get a firewall. The attempt to save information by duplicating it creates a conflict with the smoothness of space-time. Susskind refined complementarity. In response, he emphasized that the duplication is not physical copying. It is perspective-dependent description. The information exists once, but it can be described using two different sets of variables. One appropriate for the distant observer, and one for the infalling observer. These descriptions are related by a complex mathematical transformation, far more complex than ordinary coordinate changes in relativity. Think of it as describing a three-dimensional object using different two-dimensional projections. A cube can be described by its front face, its side face, or its top face. Each projection captures some information about the cube, but not all of it. No single projection is complete, yet all projections are describing the same object. Similarly, the inside and outside descriptions of a black hole are projections of a single quantum reality. This requires information to be encoded in a fundamentally non-local way. The inside description and the outside description must be mathematically equivalent, related by a quantum transformation. This is easier to claim than to demonstrate. Finding the exact transformation, the dictionary that translates between inside and outside has been a major goal of black hole research. String theory provided some tools. The AD-CCFT correspondence, which we will explore, later gives an explicit example where a gravity theory in one spacetime can be completely described by a quantum field theory on the boundary. This is complementarity made mathematically precise. The boundary theory and the bulk theory are exact translations of each other. Calculate anything in one, and you can derive the corresponding result in the other. Whether real black holes in our universe, which do not live in anti-Dieter space, follow similar rules remains uncertain. DCFT is a powerful tool, but it applies to a specific type of universe with unusual geometry. Extending the lessons to realistic black holes requires assumptions and approximations. Still, it proves complementarity is not just hand-waving. Under certain conditions, two seemingly incompatible descriptions can be precise equivalent. Black hole complementarity forces us to abandon the idea that there is one true description of reality. Instead, reality is constructed from complementary perspectives, each valid within its domain. This might seem unsatisfying, but it aligns with the spirit of quantum mechanics. The universe does not have to conform to our intuitions about objective reality. It can be stranger than that. Chapter 10 equals E bar. In 2013, Leonard Susskind and Juan Maldacena proposed one of the boldest ideas in theoretical physics. They suggested that quantum entanglement and wormholes are the same thing. When two particles become entangled, they are connected by a microscopic wormhole through space-time, This ER equals EPR conjecture links Einstein-Rosen bridges, the original name for wormholes, with Einstein-Podolsky-Rosen entanglement. Wormholes are solutions to Einstein's equations, tunnels through space-time that connect distant regions. In principle, you could enter one end and emerge at the other, bypassing the space in between. Most wormholes in general relativity are unstable, collapsing before anything can pass through, or they require exotic matter with negative energy to hold them open. They remain theoretical curiosities. Entanglement, meanwhile, is a confirmed quantum phenomenon. Entangled particles share a quantum state such that measuring one instantly determines the state of the other. This connection persists across any distance. Entanglement is used in quantum computing and quantum cryptography. It is real, tested, and understood within quantum mechanics. Susskind and Maldacena realized these two phenomena might be manifestations of the same underlying reality. An entangled pair of particles is connected by a non-traversable wormhole. You cannot send signals or matter through this wormhole. But the geometric connection exists. The quantum correlation between the particles is the wormhole. Geometry and quantum information are not separate. They are dual descriptions of the same thing. Applied to black holes, this changes everything. The Hawking radiation particle escaping from the horizon is entangled with its partner falling inside. According to ER equals EPR, they are connected by a wormhole. This wormhole is tiny, far smaller than any particle, but it provides a geometric link. The information does not have to mysteriously cross the event horizon. It flows through the wormhole connecting the two particles. As more particles radiate away, more wormholes form, linking the interior to the exterior radiation. The black hole's interior becomes connected to the outside through a vast network of microscopic wormholes. These connections might allow information to gradually leak out in a way that respects both quantum mechanics and the smoothness of space-time. No firewall is needed. The entanglement handles information transfer through geometric connections. This is speculative but mathematically suggestive. In the AD-CFT correspondence, calculations have shown that creating entanglement between two regions can make a wormhole appear connecting them. Conversely, a wormhole implies entanglement between the regions it connects. The psi-time relationship appears to hold precisely in these carefully studied examples. Whether it extends to real black holes in our universe requires assumptions. AD-CFT applies to a simplified universe with negative cosmological constant, unlike our universe which has a slight positive cosmological constant. Extrapolating from AD-CFT to reality is not straightforward. Yet the fact that ER equals EPR works exactly in at least some cases suggests it might be a fundamental principle. One implication is that spacetime geometry might be emergent from entanglement. Instead of entanglement being a phenomenon that happens in spacetime, spacetime itself might be woven from quantum entanglement. Pull on the entanglement structure and spacetime stretches. Break entanglement connections and spacetime tears. Geometry is not fundamental. Quantum information is fundamental, and geometry arises from its patterns. This flips our usual understanding. We think of particles existing in space and becoming entangled through interactions. ER equals EPR suggests particles exist. Entanglement creates geometric connections between them, and space itself emerges from the network of these connections. Without entanglement, there would be no space, no distance, no geometry. Testing this proposal is extraordinarily difficult. We cannot see microscopic wormholes. We cannot directly probe the quantum structure of spacetime, but we can test predictions. If ER equals EPR is correct, certain quantum error correction properties should appear in gravitational systems. Some of these predictions are being explored using quantum computers that simulate toy models of gravity. Another implication involves quantum communication. If entanglement creates wormholes, then quantum teleportation, a process where quantum states are transferred using entanglement, might have a geometric interpretation. You are not just transferring information through abstract quantum channels. You are sending it through space-time shortcuts. This remains speculative, but it hints at deep connections between quantum information theory and the structure of space-time. ER equals EPR also offers a new perspective on the firewall paradox. The monogamy of entanglement seems to forbid a particle from being entangled with two systems at once. But if entanglement is equivalent to geometric connections, the restriction might not apply in the same way. A particle could be connected to multiple systems through a network of wormholes that merge and split in higher dimensional spaces. The geometry is more flexible than simple entanglement rules suggest. This conjecture remains unproven. It is a proposal, an idea that fits with some calculations and extends principles we think might be true. Whether ER equals EPR is fundamentally correct or just a useful approximation will require more work. But it exemplifies how the information paradox forces physicists to reconsider the most basic elements of reality. Space, time, and quantum information might be far more deeply intertwined than anyone suspected. Chapter 11. Soft Hair. Stephen Hawking spent much of his later career searching for a way to resolve the information paradox without sacrificing his own equations. In 2016, he proposed soft hair, invisible quantum signatures on a black hole's event horizon that might store information. The name comes from a no-hair theorem in black hole physics, which states that black holes are characterized only by mass, charge, and spin. Everything else, all the hair falls off. Hawking suggested there might be soft hair, quantum features we had overlooked. The idea builds on work by Andrew Stroinger. Photons and gravitons, particles of light and gravity, can have very low energy, almost zero. These soft particles create infinite dimensional families of states at the horizon. Each state differs subtly in how particles are arranged. Black holes that look identical at high energies with the same mass and spin could differ in their soft particle arrangements. These differences are invisible to ordinary measurements but encode information. Imagine two black holes formed from different initial configurations. One from a collapsed star, another from colliding neutron stars. Classically, if they have the same mass and spin, they are identical. No experiment can tell them apart. Soft hair suggests that quantum mechanically they differ. The pattern of soft photons and gravitons around the horizon reflects their different histories. This pattern carries information about what fell in. The soft hair is not localized. It is spread across the entire horizon encoded in collective properties of the quantum field. This makes it hard to measure and hard to visualize. You cannot point to a spot on the horizon and say the information is there. It is everywhere and nowhere, woven into the quantum state of the electromagnetic and gravitational fields surrounding the black hole. When Hawking radiation is emitted, it are incredibly tiny. Far below anything we have ever seen are incredibly tiny. Far below anything we could detect with foreseeable technology. but in principle, they are there, allowing information to escape encoded in quantum patterns. Critics of soft hair point out that it is unclear whether these soft modes carry enough information. A black hole can swallow enormous amounts of matter, complex structures with vast formational content. Can patterns of soft photons and gravitons really encode all of it? The calculations are difficult. The soft hair represents an infinite dimensional space of possibilities, which is promising, but whether it has enough dimensions to hold all the information remains an open question. Another issue is whether the soft hair remains independent of the radiation. If the hair and the radiation are entangled, then information might be duplicated, leading back to the firewall problem. If they are not entangled, it is unclear how the radiation acquires the information. The mechanisms by which soft hair influences Hawking radiation need to be worked out in detail. Hawking's proposal was incomplete when he died in 2018. He and his collaborators had sketched the idea, but had not provided a full resolution of the paradox. Still, soft hair opened a new avenue of research. It suggested that black holes might not be as simple as the no-hair theorem implies. They have hidden structure, quantum features that classical gravity cannot see. This connects to the holographic principle. If information is encoded on the horizon, soft hair might be part of the encoding mechanism. The horizon is not a blank surface. It is rich with quantum degrees of freedom, patterns of fields that hold data. Soft hair could be the language in which this data is written. Whether soft hair alone can solve the information paradox is doubtful. Most physicists see it as a piece of a larger puzzle. It might work in conjunction with other mechanisms like entanglement between radiation particles or geometric connections through wormholes. Multiple effects might contribute to information escape, each carrying part of the total information. Hawking's final work on black holes shows how the paradox continued to obsess him. He had created the problem with his 1974 calculations. He spent the rest of his life trying to solve it, changing his views multiple times. First, he believed information was destroyed. Later, he accepted it must be preserved, but struggled to explain how. Soft hair was his last attempt, a suggestion that the answer lay in subtle quantum effects we had not yet appreciated. The information paradox remains unsolved, but proposals like soft hair illustrate progress. Physicists are no longer stuck arguing whether information escapes. The consensus has shifted toward information preservation. The challenge now is explaining the mechanism in detail, finding the mathematical framework that makes everything consistent. Soft hair might be part of that framework, or it might be a stepping stone towards something deeper. Chapter 12. The Page Curve. In 1993, Don Page calculated how information should escape from a black hole if quantum mechanics is correct. He plotted the entropy of the Hawking radiation over time, creating what is now called the Page curve. This curve has become a critical test for any proposed solution to the information paradox. If a theory does not reproduce the Page curve, it fails to conserve information properly. Initially, when a black hole starts radiating, the entropy of the emitted radiation increases. Each new particle adds entropy. The radiation looks random and thermal, carrying no information about what fell into the black hole. This is the early phase, and it matches Hawking's original calculations. The radiation is uncorrelated, and the entropy grows linearly with time. Halfway through the black hole's evaporation, something must change. This is the Page time, Beyond this point, the entropy of the radiation must stop increasing and start decreasing. Why? Because information is escaping. The later radiation is correlated with earlier radiation in subtle ways that reduce the total entropy. The system is transitioning from pure thermal emission to information-rich emission. By the time the black hole evaporates completely, the entropy of the radiation must match the entropy of whatever originally fell in. Information has been conserved. The radiation, if you could analyze it with infinite precision, would allow you to reconstruct everything that fell into the black hole. The page curve plots this transition, showing entropy rising, peaking at the page time and then falling back down. For decades, no one could calculate the page curve from first principles. Hawing's semi-class calculations treating gravity classically and matter quantum mechanically gave an entropy that kept increasing forever, violating information conservation. This was the heart of the paradox. Pau's curve showed what should happen. Deriving it from theory required understanding quantum gravity. In 2019 and 2020, breakthroughs came. Physicists, using the AD-CFT correspondence and related tools, calculated the entropy of Hawking radiation, including quantum corrections to the geometry. They found that the page curve emerged naturally. The entropy peaked and then decreased exactly as Page predicted. This was hailed as major progress, the clearest sign yet that information is preserved. The key insight involved islands. These are regions inside the black hole that contribute to the entropy calculation in surprising ways. When you carefully account for quantum entanglement between the interior and the radiation, certain regions inside the horizon, the islands must be included in the entropy formula. This changes the result dramatically, causing the entropy to decrease after the page time. Islands are mathematical constructs, not physical places. They represent how information is distributed across space-time when quantum effects are included. The existence of islands suggests that the interior and exterior of the black hole are not as separate as classical relativity implies. They are entangled in ways that allow information to flow from one to the other. These calculations were done in simplified models, toy universes with special symmetries that make the math tractable. Whether the same mechanisms work in realistic black holes in our universe is not yet proven, but the fact that the page curve emerges in any consistent quantum gravity calculation is a powerful clue. It suggests the resolution of the paradox is not exotic. It follows from properly accounting for quantum mechanics in curved spacetime. The page curve also sets a timeline for information escape. Information does not start escaping immediately. For the first half of the black hole's evaporation, the radiation is essentially random. Only in the second half does information begin leaking out. An observer trying to reconstruct what fell in would need to collect radiation from both phases and analyze correlations between early and late emissions. This delayed escape has implications. If you throw a book into a black hole, the information in that book is trapped until the page time. For a large black hole, this could be billions or trillions of years. The information is not destroyed, but it is inaccessible for an extraordinarily long time. From a practical standpoint, it might as well be destroyed. Yet the principle matters. In principle, the information survives. The page curve is now a benchmark. Any proposed resolution of the information paradox must reproduce it. Theories that predict ever-increasing entropy fail. Theories that have information escaping too early or too late also fail. The curve is a precise target, and hitting it requires getting the quantum, mechanics and gravity exactly right. Recent successes in deriving the curve suggest we are converging on the correct answer. Chapter 13. Islands in the Entropy. The island formula is one of the most surprising recent discoveries in black hole physics. It emerged from attempts to calculate the entropy of Hawking radiation precisely, including quantum corrections. The result was shocking. To compute the entropy of radiation outside the black hole, you must sometimes include regions inside the black hole in your calculation. These regions are called islands. This seems nonsensical at first. How can the entropy of radiation outside depend on regions inside the event horizon? The horizon is supposed to be a one-way membrane. Information inside cannot affect the outside. Yet, the math insists otherwise. When you properly account for quantum entanglement, the boundary between inside and outside becomes blurry. The island formula works like this. You want to calculate the entropy of the E-jet Hawking radiation. Normally, you would sum over all possible quantum states the radiation could be in. But when gravity is involved, you must also consider the gravitational field's quantum states. This includes the geometry of spacetime itself. Some configurations of spacetime create quantum correlations between the radiation and regions inside the black hole. These interior regions, the islands, become entangled with the radiation. When calculating entropy, entangled systems must be treated together. You cannot calculate the entropy of the radiation alone. You must include the island. Surprisingly, this inclusion reduces the total entropy. The entanglement between the island and the radiation means they share information, decreasing the entropy of the combined system. As the black hole evaporates, the island grows. Initially, there is no island. The entropy calculation includes only the radiation, and entropy increases. At the page time, an island suddenly appears in the entropy formula. From then on, the island grows, and the total entropy decreases. By the time the black hole has completely evaporated, the island has encompassed the entire former interior, and the entropy has returned to the initial value. This is deeply strange. It suggests that the interior and exterior of a black hole are not separate systems. They are quantum mechanically entangled in a way that allows information to flow between them. Even though classically they are causally disconnected, the island is not a physical object you could visit. It is a feature of how quantum information is distributed across space-time. Critics ask what islands physically represent. Are they just mathematical tricks, artifacts of the calculation method, or do they reveal something profound about quantum gravity? The answer seems to be the latter. Islands emerge naturally when you include quantum corrections to gravity. They are not put in by hand. They are required by consistency. The existence of islands validates the holographic principle. If the interior is entangled with the exterior, then information about the interior can be encoded on the boundary. The horizon acts as a holographic screen, storing data about everything inside in its quantum state. Islands show how this encoding changes over time as the black hole radiates. Islands also resolve the firewall paradox, at least partially. The monogamy of entanglement seemed to require a firewall because radiation particles needed to be entangled with two systems simultaneously. Islands show that the interior is not a separate system. It is entangled with the radiation. The radiation and the interior are part of a single quantum state, eliminating the need for a firewall. Calculating islands requires advanced techniques from quantum information theory and quantum gravity. Physicists use the replica trick, a method where they mathematically copy the universe multiple times and analyze the copies to extract entropy. This sounds bizarre, but it is a standard tool in quantum field theory adapted for gravitational systems. Islands have been calculated in many toy models, universes with simplified physics where the math is manageable. They consistently reproduce the page curve showing entropy decreasing after the page time. Extending these calculations to realistic black holes in four-dimensional spacetime remains a challenge. The tools work best in two-dimensional models or in ad space with special symmetries. Despite these limitations, islands represent conceptual progress. They show that quantum mechanics and gravity can coexist if we think carefully about entanglement and geometry. The interior of a black hole is not isolated. It is quantum mechanically connected to the radiation, allowing information to escape in ways classical thinking would not permit. The island formula is still being refined. New papers appear regularly, extending the calculations to more realistic scenarios, testing the formula's limits, and exploring its implications. Some physicists believe islands are the key to resolving the paradox completely. Others see them as one piece of a more complex puzzle. Either way, they have shifted the conversation. We are no longer debating whether information escapes. We are working out the details of how. In 1997, Juan Muldacena discovered a startling relationship between two seemingly unrelated theories. A theory of gravity in a higher dimensional curved space called anti-to space is exactly equivalent to a quantum field theory without gravity living on the boundary of that space. This ADC-CFT correspondence is the most concrete realization of the holographic principle, and it has become a crucial tool for studying black holes. Anti-diameter space has unusual geometry. It curves with negative curvature like a saddle surface extending infinitely. It is not the space we live in. Our universe has positive curvature from dark energy. But AD space is mathematically simpler, allowing physicists to solve problems that are intractable in realistic settings. The boundary of AD space is one dimension lower. A three-dimensional AD space has a two-dimensional boundary. The quantum field theory on the boundary, called a conformal field theory, has no gravity at all. It is a theory of particles and forces like the theories describing electromagnetism or the strong nuclear force. Yet every calculation in this boundary theory corresponds exactly to a calculation in the higher dimensional gravity theory, create a black hole in the bulkhead space, and it manifests as a hot thermal state in the boundary theory. The black hole in gravity language is a temperature in quantum language. This duality is exact, not an approximation. Any question you can ask about the gravity theory can be translated into a question about the boundary theory and vice versa. This is profound. It means gravity in the bulk is not fundamental. It is emergent from the quantum interactions on the boundary. Spacetime itself is a hologram projected from quantum information living in fewer dimensions. For the black hole information paradox, AD-CFT provides a definitive answer. The boundary theory is an ordinary quantum field theory. Quantum field theories always conserve information. Therefore, the corresponding black hole in the bulk must also conserve information. Information cannot be destroyed in the boundary theory. So, it cannot be destroyed in the gravity theory either. The paradox is resolved by the existence of the duality. This sounds like cheating. We have not explained how information escapes from the black hole. We have just asserted it must because the boundary theory says so. But ADCFT is more than assertion. Physicists have explicitly calculated how information escapes by translating black hole processes into boundary theory language. The Hawking radiation corresponds to correlations in the thermal state. These correlations encode information about what created the black hole. The Page curve emerges naturally in ADCFT. Calculate the entropy of the Hawking radiation using the boundary theory, and you get a curve that rises and then falls. The entropy is the entanglement entropy between the radiation and the remaining black hole. As the black hole evaporates, entanglement shifts from interior to exterior, causing the entropy to decrease. Islands, when properly included, appear in the calculation and ensure the curve has the correct shape. ADCFT also clarifies black hole complementarity. The interior and exterior descriptions correspond to different ways of organizing the boundary theory. Both are valid, describing the same underlying quantum state from different perspectives. The translation between them is highly non-local and complex, explaining why the two descriptions seem incompatible. The catch is that ADS CFT applies to a universe that is not ours. Antidesa space is infinite and has a boundary. Our universe is expanding finite in spatial extent at any given time and has no boundary. Extending the lessons from ADS to realistic black holes requires assumptions. We hope the insights carry over, but proof is elusive. Despite this limitation, ADCFT has revolutionized quantum gravity research. It provides a concrete example where gravity emerges from quantum mechanics. Space-time, geometry, even the dimensionality of space arise from quantum entanglement patterns in the boundary theory. This suggests that in any quantum theory of gravity, space-time should be emergent. Black holes in AD space have been studied exhaustively. Physicists have calculated their thermodynamics, their evaporation, their response to perturbations, all by translating problems into boundary theory language. These calculations reveal how quantum information flows, how entanglement evolves, and how classical geometry emerges from quantum states. Each result deepens our understanding of how quantum mechanics and gravity fit together. Some physicists believe ADCCFT is more than a tool. It might be a template. Perhaps every universe has some kind of holographic jewel, some lower-dimensional quantum theory that encodes all gravitational physics. If so, finding the dual for our universe would solve quantum gravity completely. We could calculate anything about spacetime by working in the simpler quantum theory. ADCFT does not directly tell us what happens at the singularity inside a black hole. The boundary theory does not have an obvious interpretation of the singularity. This remains mysterious. But for questions about information horizons and evaporation, ADCCFT has been spectacularly successful. It proves that information is preserved and offers a framework for understanding how calculating entropy in quantum systems is notoriously difficult. Entropy measures the uncertainty or disorder in a quantum state. But extracting this number from the mathematics often requires clever tricks. One such trick, called the replica method, has become essential for studying black hole evaporation. The idea is to make multiple copies of the universe, analyze the copies, and use the results to deduce properties of the original. Start with a quantum state describing the universe, including a black hole and its radiation. You want to know the entropy of the radiation. Directly calculating this entropy is too hard. Instead, you create two identical copies of the universe. Now, calculate the overlap between these copies, a measure of how similar they are. Repeat this process for 3 copies, 4 copies, and so on. These overlaps encode information about the entropy. The replica trick extracts entropy by analyzing how the overlaps change as you vary the number of copies. Mathematically, you compute a function called the partition function for different numbers of replicas, then use a formula to derive the entropy. This method was developed in statistical mechanics decades ago, but applying it to quantum gravity is new and requires modifications. In the context of black holes, the replica trick involves copying not just the quantum state, but also the geometry of space-time. Each replica has its own black hole, its own horizon, its own interior. These replica spacetimes can connect to each other in strange ways. The connections create what are called replica wormholes, geometric links between different copies of the universe. These replica wormholes are not physical. You cannot travel through them. They appear only in the mathematical calculation, but they affect the result dramatically. When replica wormholes are included, the entropy calculation changes. The dominant contribution to the partition function comes from geometries where the replicas are connected. This connection introduces islands into the entropy formula. Without replica wormholes, the entropy increases forever, matching Hawking's original calculation. With replica wormholes, the entropy follows the page curve, rising and then falling. The replica trick reveals that quantum gravity includes geometric configurations. Hawking did not consider these configurations encode information flow from interior to exterior. The mathematics is abstract and technical. Physicists must sum over all possible geometries that connect the replica universes, weighing each geometry by its probability. This is a path integral over spacetime geometries, a central concept in quantum gravity. The path integral includes geometries with wormholes, geometries without them, and everything in between. The calculation determines which geometries dominate. Replica wormholes sound exotic, but they are natural consequences of treating geometry quantum mechanically. In quantum mechanics, particles can tunnel through barriers, appearing on the other side without crossing the space in between. Similarly, in quantum gravity, space-time can tunnel between different configurations. Replica wormholes are one such tunneling process, linking different replica geometries. The replica trick works beautifully in two-dimensional models and in ADCFT. These are simplified scenarios where calculations can be completed. Extending the method to four-dimensional black holes in realistic space-time is harder. The mathematics becomes overwhelmingly complex, but partial results suggest the replica trick will work there too, reproducing the page curve and resolving the paradox. Critics of the replica method question whether it is physically meaningful or just a mathematical tool. If replica wormholes appear only when you artificially copy the universe, do they tell us anything real? Proponents argue that the replica trick is no different from other quantum calculation methods. The replicas are scaffolding that allows us to compute physical quantities. The final result? The entropy is real and measurable in principle. The success of the replica trick in deriving the page curve has convinced many physicists that information is preserved. It provides an explicit mechanism, albeit a mathematical one, by which information escapes. The islands that emerge from replica wormholes show how entanglement between the interior and radiation changes over time, allowing information to leak out gradually. The replica trick also connects to other ideas in quantum gravity. The geometries that contribute to the path integral can be interpreted as different quantum states of spacetime. Some states have horizons, others do not. Some have singularities, others resolve them. By summing over all these states, quantum gravity averages over many possible geometries, smoothing out the paradoxes that arise in any single classical geometry. Understanding the replica trick requires comfort with advanced quantum field theory and general relativity. It is not intuitive, but it represents the cutting edge of black hole research. The next generation of breakthroughs will likely build on these techniques, refining them and extending them to more realistic situations. The replica trick is a glimpse of how quantum gravity calculations will be done in the future. Unitarity is a technical term in quantum mechanics that means something simple but profound. Evolution is reversible. If you know the quantum state of a system at one time, you can calculate its state at any other time, forward or backward. No information is lost. This reversibility is baked into the equations of quantum mechanics. Break unitarity, and the entire theory collapses. Every experiment ever performed confirms unitarity. Particles collide, interact, and scatter. Measure them carefully enough, and you find all the information about the initial state is preserved in the final state. It might be scrambled, hidden in subtle correlations, but it is there. Quantum mechanics never destroys information. It only transforms it. Black holes seem to violate this. Hawing's calculation showed that the radiation emitted by a black hole is random, carrying no information about what fell in. When the black hole evaporates completely, the initial pure state, say a specific collection of atoms forming a book, has become a mixed state of random radiation. Pure states have zero entropy. Mixed states have positive entropy. The transition from pure to mixed is non-unitary. Information has been destroyed. This is not a small problem. If unitarity fails for black holes, why should it hold anywhere else? What makes black holes special? Maybe unitarity is only approximate breaking down in extreme conditions. But then all of quantum mechanics becomes suspect. Predictions that rely on unitarity, like the stability of atoms or the behavior of quantum computers, might be wrong in ways we have not noticed. Physicists overwhelmingly believe unitarity must hold. The alternative is too radical. Quantum mechanics is the most successful theory in the history of science. Measured in terms of predictive accuracy, nothing comes close. Giving up unitarity to save black holes feels backward. Better to find where Hawking's calculation went wrong. Hawking treated gravity classically. He applied quantum mechanics to matter fields, but not to spacetime itself. This semi-classical approximation is valid in many situations, but perhaps not for evaporating black holes. Quantum corrections to the geometry, tiny effects ignored in Hawking's calculation, might accumulate over time. These corrections could introduce correlations in the radiation, preserving information. Proving unitarity for black holes requires calculating the full quantum state, including gravity. This is extraordinarily difficult. No one has a complete quantum theory of gravity yet, but partial calculations using tools like ADCCFT and the replica trick suggest unitarity holds. The page curve derived from these methods is a unitary curve. Entropy rises and falls, indicating reversible evolution. The firewall paradox threatened unitarity in a different way. If preserving information requires burning and falling observers, then the smooth evolution predicted by general relativity is violated. Different observers experience incompatible realities. This also breaks unitarity in a sense because the quantum state becomes observer-dependent. Yet another reason physicists worked so hard to avoid firewalls. Islands and replica wormholes restore unitarity without firewalls. They show how information escapes through subtle quantum channels. The radiation only looks random if you ignore these channels. Include them, and correlations appear. The final state is pure, not mixed. Unitarity is preserved. Black holes are strange, but they do not break the fundamental rules of quantum mechanics. Unitarity also implies something about the singularity. If information is never destroyed, the singularity cannot destroy information either. This suggests the singularity is not a true endpoint. Perhaps it is replaced by a quantum structure, a Planck star, or a fuzzball that stores information and eventually releases it. Or perhaps the singularity is unphysical, an artifact of pushing classical equations beyond their domain of validity. Demanding unitarity has been a guiding principle throughout this research. When faced with a choice between modifying quantum mechanics and modifying gravity, most physicists modify gravity. Gravity is less tested in extreme regimes. Quantum mechanics has passed every test. Unitarity is not negotiable. Any theory of quantum gravity must preserve it. In this sense, the information paradox has been a gift. It forced physicists to develop new tools, explore new ideas, and deepen their understanding of both quantum mechanics and gravity. The paradox revealed where our theories were incomplete. Solving it will complete them, giving us a unified framework that describes nature at every scale. Unitarity demands it. The universe must make sense. Quantum mechanics forbids making perfect copies of unknown quantum states. This is the no-cloning theorem, proven in the 1980s. If you have a particle in an unknown state, you cannot create an exact duplicate without destroying the original. The information cannot be copied. It can only be moved. This theorem protects information in quantum systems, preventing duplication and ensuring uniqueness. The no-cloning theorem connects to the black hole paradox in a subtle way. If information falling into a black hole is encoded on the horizon, as the holographic principle suggests, then the information exists in two places simultaneously. Inside, carried by the infalling matter, and outside, scrambled across the horizon. This looks like cloning the same information duplicated. Quantum mechanics forbids it. Black hole complementarity attempts to resolve this by saying the two descriptions are not simultaneous from any single observer's perspective. The outside observer sees information on the horizon, but never sees it inside. The infalling observer sees information inside but does not perceive it on the horizon. Since no observer sees both, no cloning occurs. The duplication is an artifact of combining perspectives that cannot be compared. This argument is clever but controversial. It relies on the assumption that reality is observer-dependent in a strong sense. If information objectively exists in two places, even if no single observer can verify both, that still seems like cloning. Quantum mechanics forbids cloning regardless of whether anyone notices. The firewall paradox amplifies this issue. If escaping radiation carries information out, and the infalling observer carries the same information inside, then the information is genuinely duplicated during some phase of evaporation. The no-cloning theorem seems violated. To avoid this, something must break. Either the information is not truly in both places, or the infalling observer does not smoothly cross the horizon. Islands provide a different resolution. They suggest information is not duplicated. Instead, The entanglement between the interior and the radiation means the information is shared, not copied. The interior and the radiation are parts of a single quantum state. Asking where the information is located becomes meaningless. It is spread across both regions in an entangled way that does not violate no cloning. Think of entangled particles. Measure one and you instantly know the state of the other. The information about their combined state is not localized in either particle. It exists in the correlation between them. Similarly, information in a black hole system might exist in correlations between the interior and the radiation, not in either place individually. No cloning occurs because the information was never fully in just one place to begin with. This is deeply non-local. Information is not a property of individual particles or regions. It is a property of the global quantum state. Locality, the idea that distant regions are independent, breaks down. Quantum mechanics has always been non-local in the sense of entanglement. But black holes make this non-locality extreme. Information cannot be pinned to a location. It is fundamentally distributed. The no-cloning theorem also constrains time travel scenarios involving black holes. If you could send information into a black hole and retrieve it through Hawking radiation, you might create a copy, violating no cloning. This suggests certain types of closed time-like curves, paths through spacetime that loop back in time, cannot exist in a universe that obeys quantum mechanics. The topology of spacetime is restricted by quantum information theory. Some physicists have explored whether the no-cloning theorem could be weakened in gravitational contexts. Maybe quantum gravity allows approximate cloning, creating imperfect copies that are close but not exact. These imperfect copies might carry less than the full information, skirting the theorem's strict prohibition. However, such modifications would have to be incredibly subtle to avoid contradicting experiments. Most researchers believe no, cloning remains sacred. It is tied too deeply to the structure of quantum mechanics to be altered. Instead, our understanding of where and how information is stored must change. Black holes teach us that information is not localized the way we intuitively think. It is relational, contextual, and fundamentally quantum mechanical. The interplay between no cloning and black holes highlights a tension between quantum mechanics and spacetime. Quantum mechanics treats information as primary. Spacetime treats location as primary. In quantum gravity, this tension must be resolved. Perhaps information is fundamental and spacetime emerges from it. The no-cloning theorem would then be a principle about the structure of reality, not just a quirk of quantum particles. Understanding black holes requires rethinking everything: space, time, information, and even what it means for something to exist in a place. The no-cloning theorem is one thread in this tapestry. Pulling on it unravels our assumptions about reality. What if information does not escape through Hawking radiation at all? What if it tunnels into tiny pocket universes that branch off from our own? This is the baby universe proposal. A speculative but mathematically consistent idea. When a black hole evaporates, quantum effects might create microscopic wormholes connecting our spacetime to newborn universes. Information flows through these wormholes, disappearing from our universe entirely. In quantum gravity, spacetime can fluctuate wildly at the smallest scales. Virtual black holes pop in and out of existence. Wormholes appear and vanish. The fabric of reality is foamy, turbulent, nothing like the smooth geometry we experience at large scales. Some of these quantum fluctuations might be stable enough to grow into separate universes connected to ours by thin threads of space-time. A baby universe starts microscopic, smaller than an atom. It has its own space, its own time, its own physical laws, potentially different from ours. The connection to our universe is a wormhole, but not the traversable kind from science fiction. This wormhole is dynamic, quantum mechanical, and collapses almost immediately. Yet, during its brief existence, quantum information can flow through. When matter falls into a black hole, instead of piling up at the singularity, it might tunnel through a quantum wormhole into a baby universe. The information is not destroyed. It is relocated. From our perspective, it disappears. The black hole evaporates, releasing random radiation with no information. The paradox seems to return, except information still exists, just not in our universe anymore. This sounds like giving up. If information escapes to another universe, we can never verify it. We can never test whether baby universes exist. They are causally disconnected from us. No signal can return from a baby universe to confirm it is there. This makes the proposal unfalsifiable, which troubles many physicists. Science requires testable predictions. Baby universes make none. Defenders argue that the mathematics predicts baby universes naturally. In certain formulations of quantum gravity, they appear as solutions to the equations. Ignoring them because they are untestable seems arbitrary. The equations tell us what exists, even if we cannot observe it directly. Besides, many aspects of modern cosmology, like the interior of black holes or regions beyond the cosmic horizon, are also untestable but still considered real. Baby universes affect our universe in subtle ways. The wormholes connecting us to them might alter the effective constants of nature. Physical constants like the mass of the electron or the strength of gravity could fluctuate slightly depending on how many baby universes branch off. These fluctuations are incredibly tiny, far below current measurement precision, but they exist in principle. Some versions of the baby universe idea suggest they eventually reconnect to our universe at different space-time locations. A black hole in one region might be connected through a baby universe to a white hole elsewhere, an object that spews matter out instead of sucking it in. White holes are solutions to Einstein's equations, but have never been observed. If baby universes link black holes to white holes, information could return to our universe far in the future or in distant locations. This reconnection would preserve information globally while violating local unitarity. Information disappears from one region and reappears in another without traveling through the space between them. The universe as a whole remains unitary, but local patches do not. Observers in one region see information destroyed. Observers in another region see it created from nothing. Only by accounting for the entire universe, including baby universes, does everything balance. Critics point out this still violates the spirit of unitarity. Quantum mechanics is supposed to be local in the sense that what happens here should be determined by conditions nearby, not by distant baby universes. Allowing information to jump across disconnected spacetimes feels like abandoning locality altogether. It replaces one mystery with another. The baby universe proposal highlights a deep question. Does information have to stay in our universe? Or is the multiverse a collection of all possible universes the proper arena for information conservation? If baby universes are real, then our universe is not closed. It leaks information into other universes, and perhaps receives information from elsewhere. The total information across all universes is conserved, but not within any single universe. This connects to the landscape problem in string theory. String theory predicts a vast number of possible vacuum states, each corresponding to a different universe with different physical laws. Baby universes might be realizations of these other vacua branching off from ours through quantum processes. The multiverse becomes a dynamic network where universes birth other universes continuously. Whether baby universes actually exist depends on the correct theory of quantum gravity. In some approaches, like loop quantum gravity, they do not naturally appear. In others, like string theory with certain assumptions, they do. Experimental evidence for baby universes is non-existent. We cannot see them, detect them, or interact with them. They remain theoretical constructs, solutions to equations that may or may not describe reality. The baby universe proposal reminds us how strange quantum gravity might be. Our intuitions about information, locality, and causality may not apply. The universe might be far weirder than we imagine, with hidden dimensions, branching timelines, and information flowing through invisible channels. Black holes are windows into this strangeness, showing us where our current theories break down and where new physics must enter. Quantum computers are fragile. Quantum information decays easily, corrupted by noise and interference. To protect it, physicists developed quantum error correction, encoding information redundantly, so errors can be detected and fixed without directly measuring the fragile quantum state. Surprisingly, this same mathematical structure appears in quantum gravity. Space-time itself might be a quantum error-correcting code. The basic idea of quantum error correction is to spread information across multiple particles. Instead of storing one bit of information in one particle, you store it in several particles using clever entanglement patterns. If one particle gets corrupted, the information can be recovered from the others. The code is designed so that measuring the error does not destroy the encoded information. In 2014, physicists realized that the ADS-CFT correspondence has the structure of a quantum error-correcting code. The boundary theory encodes information about the bulk spacetime redundantly. You can lose access to part of the boundary, and the full bulk information is still recoverable from the remaining part. This redundancy is not accidental. It is how holography works. Think of it this way. The bulk spacetime is the information you want to protect. The boundary theory is the code. Disturbances in the bulk, like throwing matter into a black hole, correspond to encoding operations. The horizon acts as the error, blocking access to part of the information. Yet, quantum error correction ensures the information is not truly lost. It can be reconstructed from the Hawking radiation using the code. This perspective explains why information is preserved. Black holes do not destroy information because spacetime itself is designed to protect it. The geometry of the horizon, the entanglement between interior and exterior, the patterns of Hawking radiation are all features of an error-correcting code. Information falling into a black hole is like information corrupted by noise in a quantum computer. The code allows recovery. Quantum error correction also clarifies complementarity. Different observers, the infalling and the distant, are accessing different parts of the code. Each sees a consistent description, but the descriptions are complementary because they correspond to different error syndromes. The code guarantees both descriptions encode the same information, just organized differently. This is why both can be correct simultaneously. The firewall paradox can be understood as a conflict between error correction and smoothness. If the horizon acts as an error, then correcting that error requires operations that might seem violent, like a firewall. However, clever code design can correct errors smoothly without disrupting the quantum state. The challenge is finding the code structure that allows smooth error correction at a black hole horizon. Recent research explores what kind of codes spacetime might use. Not all quantum error correcting codes work the same way. Some are robust to many types of errors but require complex decoding. Others are efficient but fragile. The code underlying spacetime must be special, capable of protecting information while allowing smooth evolution and respecting causality. One proposal is that spacetime uses a code called a stabilizer code, similar to those used in practical quantum computers. These codes have nice mathematical properties, making them easier to analyze. If spacetime is a stabilizer code, certain predictions follow about how black holes behave and how information escapes. Physicists are working out these predictions and looking for ways to test them. Another idea is that the code structure is dynamical, changing as the black hole evaporates. Early in evaporation, the code might prioritize smoothness, allowing an observer to fall through the horizon without noticing. Late in evaporation, the code might shift to prioritize information extraction, creating conditions where information escapes more efficiently. The transition between these phases could correspond to the page time. Quantum error correction provides a language for discussing the information paradox. Instead of asking where information is located, we ask how it is encoded. Instead of worrying about cloning, we recognize that redundant encoding is how codes work. Information can be stored in multiple places without violating no cloning if the encoding is done correctly. The black hole horizon is not a barrier. It is part of the code. This framework also suggests experiments. Quantum computers can simulate toy models of black holes, implementing the error-correcting codes explicitly. Researchers have done this, creating quantum circuits that mimic black hole evaporation. These simulations allow testing whether information is preserved, whether the page curve appears, and whether different observers see complementary descriptions. So far, the results support information conservation. Quantum error correction might be the deepest lesson from the information paradox. It tells us that space-time is not fundamental but emergent from quantum information. The geometry we observe, the smooth manifold of general relativity, arises from the structure of a quantum code. Gravity is not a force acting in space-time. It is a property of how information is organized and protected. Understanding this fully would revolutionize physics. It would unify quantum mechanics and gravity at a fundamental level. The equations of general relativity would be derived from principles of quantum information theory. Black holes would be understood as regions where the code structure is most evident, where the quantum nature of space-time cannot be ignored. We are glimpsing this vision, but the full picture remains out of reach. What if black holes do destroy information, but in a controlled, deterministic way? This is the final state proposal. A controversial idea that accepts information loss but argues it does not break quantum mechanics. The trick is to assume that all evaporating black holes end in the same final quantum state, regardless of what fell in information is erased. But the erasure is predictable, preserving a form of determinism. In ordinary quantum mechanics, A pure state evolves into another pure state, a mixed state. One with uncertainty evolves into another mixed state. Pure states never become mixed because that would violate unitarity. The final state proposal breaks this rule. It allows pure states to evolve into a fixed mixed state, the final state, which is the same for all black holes. Why does this not destroy physics? Because the final state is special. It is not random. It is a specific, carefully chosen state that absorbs information without introducing contradictions. Think of it as a quantum trash can that swallows information but in a way that respects other physical laws. The process is non-unitary, but it is predictable. You can still calculate probabilities. The theory remains consistent. The final state is postulated to exist in the future after the black hole evaporates. It acts backward in time, influencing the evaporation process. This time, symmetric approach is strange but mathematically allowed in quantum mechanics. Boundary conditions in the future affect evolution in the present. The final state guides how the black hole radiates, ensuring the end point is always the same, regardless of the initial state. Critics attack this proposal from multiple angles. First, accepting non-unitary evolution feels like abandoning quantum mechanics. The success of quantum theory rests on unitarity. Allowing exceptions, even controlled ones, opens the door to chaos. If unitarity fails for black holes, why not elsewhere? What prevents non-unitary processes from appearing in ordinary quantum systems? The proposal offers no clear boundary. Second, the final state seems contrived. Why should nature impose a specific endpoint for black holes? What mechanism enforces it? The proposal does not explain where the final state comes from or why it exists. It is postulated to solve the paradox but lacks independent motivation. This feels ad hoc, invented solely to patch a problem rather than emerging from deeper principles. Third, time-symmetric quantum mechanics is controversial. Most physicists use a timemetric formulation where initial conditions are specified, but final conditions are not. Introducing final boundary conditions requires rethinking the foundations of quantum theory. Some researchers explore such reformulations, but they remain fringe. The mainstream view treats time asymmetrically. Defenders of the final state proposal argue that desperate times call for radical ideas. The information paradox resists conventional solutions. Maybe we need to modify quantum mechanics in extreme conditions. Black holes are the most extreme environments imaginable. If unitarity fails anywhere, it would fail there. The final state proposal accepts this possibility and constructs a consistent framework around it. The proposal also makes testable predictions. In principle, if the final state exists, Hawking radiation should show specific patterns, deviations from pure thermal emission that depend on the final state structure. These deviations are incredibly subtle, far beyond current observational capabilities, but they exist. Future technology, perhaps analyzing radiation from primordial black holes, if they exist, might detect them. Another argument in favor is that the final state proposal resolves all paradoxes cleanly. No firewalls, no complementarity puzzles, no islands. Information is simply destroyed in a controlled way. The black hole interior is real. The horizon is smooth. Observers fall in without drama. Everything is straightforward except for the single modification, non-unitary evolution to a fixed end point. However, most physicists reject this path. The consensus has shifted toward information preservation. Add CTF, islands, and the page curve all support conservation. These frameworks are complex, but they preserve unitarity. Abandoning unitarity seems unnecessary given that solutions respecting it appear to exist. The final state proposal is a fallback relevant only if all other approaches fail. Interestingly, the final state idea connects to other physics mysteries. The arrow of time, why the future is different from the past, might be explained by final boundary conditions. The cosmological constant problem, why dark energy has the value it does, might be related to final state constraints. If final states exist for black holes, perhaps they exist for the entire universe, shaping cosmic evolution in ways we have not recognized. The proposal remains on the fringes, studied by a small group of physicists who believe the paradox demands radical solutions. It serves as a reminder that not all physicists agree on the path forward. The information paradox has many proposed solutions and none are proven beyond doubt. The final state proposal is one option, controversial but coherent, waiting to see if mainstream approaches succeed or fail. Chapter 21. Planck Stars. At the center of a black hole, general relativity predicts a singularity where curvature becomes infinite. Quantum mechanics suggests this cannot happen. Infinity is not physical. It signals where the theory breaks down. Loop quantum gravity offers an alternative. Instead of a singularity, the collapsing matter forms a Planck star, an object of maximum density that resists further compression and eventually bounces back. The Planck density is 100 million trillion kilograms per cubic meter. Beyond this, quantum effects dominate. Space itself becomes discrete. There are no smaller volumes to collapse into. When matter reaches this density, gravitational pressure cannot overcome the quantum resistance. The collapse halts. Then quantum repulsion takes over and the matter begins expanding again. This bounce happens deep, inside the black hole, hidden behind the event horizon. From outside, nothing appears different. The black hole looks the same with its horizon intact. But inside, the singularity is replaced by a Planck star undergoing a slow-motion explosion. The star expands, eventually pushing outward against the horizon from within. Given enough time, the horizon shrinks and eventually disappears. How long does this take? For a black hole the mass of our planet, the bounce and expansion could take longer than the current age of the universe. Time dilation near the horizon makes internal processes appear frozen from outside. An observer far away would see the black hole evaporate through Hawking radiation, long before the Planck star's expansion becomes apparent. Yet, from the perspective of the star itself, the explosion is inevitable. This resolves the information paradox directly. Information never reaches a singularity because there is no singularity. It is stored in the quantum state of the Planck star, encoded in the positions and momenta of particles compressed to Planck density. As the star expands, that information is carried outward. When the horizon eventually dissolves, the information is released back into the universe. The Planck star model predicts that black holes are not eternal. They are temporary phases. Matter collapses, bounces, and re-expands. The entire process is unitary. Information is preserved throughout. The apparent event horizon is not permanent. It is a phase boundary like the surface of a star, present for a limited time before the object transforms into something else. Critics question whether quantum gravity effects are strong enough to halt collapse. General relativity's pull is immense near the singularity. Can quantum pressure really counteract it? Loop quantum gravity says yes, but the calculations are difficult and not universally accepted. The theory is still under development. Some aspects remain speculative. Another issue is reconciling the Planck star timeline with Hawking radiation. If the star takes billions of years to explode, does information escape gradually through radiation or all at once when the horizon disappears? If it is gradual, through what mechanism does information leak out before the explosion? If it is all at once, how do we explain the page curve, which suggests gradual information release starting at the page time? Some researchers propose that quantum corrections modify the horizon, creating small gaps or fluctuations that allow information to escape even while the Planck star is trapped inside. These gaps would be incredibly small, but over long time scales, they could leak significant information. The Planck star and Hawking radiation would work together, both contributing to information release. Observationally, Planck stars are challenging to detect. They are hidden inside black holes. The explosion, when it happens, might produce a burst of radiation, but distinguishing it from other astrophysical events is hard. If tiny primordial black holes exist, formed in the early universe, some might be nearing the end of their lifetimes. Detecting their explosions could provide evidence for Planck stars. The Planck star idea also affects our understanding of the universe's fate. If black holes do not last forever, then the far future looks different. Instead of an eternally dark cosmos filled with slowly evaporating black holes, we might have periodic explosions as Planck stars erupt. These events could inject energy and matter back into the universe, potentially enabling new cycles of structure formation. Philosophically, Planck stars are appealing. They avoid singularities, those troubling infinities where physics fails. They preserve information naturally without needing complex encoding schemes or observer-dependent realities. The universe remains deterministic and unitary. What appears to be destruction, the collapse into a black hole, is actually transformation, a compression followed by eventual release. Whether Planck stars are real depends on whether loop quantum gravity is correct. If space-time is fundamentally discrete at the Planck scale, then Planck stars are inevitable. If some other approach to quantum gravity is correct, the singularity might be resolved differently or perhaps not at all. The information paradox pushes us to answer these deep questions about the nature of space-time. Chapter 22. Bekenstein-Hawking Entropy. In the early 1970s, Jacob Bekenstein proposed something audacious. Black holes have entropy. This was shocking because entropy measures disorder in thermal systems, and black holes were thought to be perfectly ordered, characterized only by mass, charge, and spin. Bekenstein argued that the area of the event horizon measures the black hole's entropy. Bigger horizon means more entropy. Stephen Hawking initially resisted this idea. Entropy implies temperature, and temperature implies radiation. Black holes do not radiate in classical physics, but when Hawking calculated quantum effects near the horizon, he found Bekenstein was right. Black holes have temperature. They radiate. Their entropy is proportional to horizon area, not volume. The formula is simple and exact. Entropy equals 1/4 the horizon area measured in Planck units. This relationship is strange. Ordinarily, entropy grows with volume. A box of gas twice as large has twice the entropy. But a black hole twice as massive has 4 times the horizon area because area scales with radius squared. This suggests black hole entropy is fundamentally different from ordinary matter entropy. It suggests information is stored on the surface, not in the volume. Bekenstein-Hawking entropy is enormous. A black hole, the mass of our planet, has entropy exceeding the entire observable universe's entropy. If the universe were compressed into a box that size, black holes are the most efficient entropy storage devices allowed by physics. This makes them important for understanding thermodynamics at cosmic scales. The entropy formula implies a maximum amount of information that can fit in a region. Take any volume of space. The maximum entropy it can contain is achieved by forming the largest black hole that fits inside. Anything more, and the black hole would be bigger, exceeding the volume. This Bekenstein bound limits information density everywhere, not just in black holes. This connects to the holographic principle. If a black hole's entropy depends on surface area, perhaps all information in any volume is encodable on its boundary. The three-dimensional interior is redundant. Everything that happens inside can be described by data on the surface. The universe is a hologram with black holes as the clearest examples. Bekenstein-Hawking entropy also drives the information paradox. If entropy measures information, and a black hole's entropy is proportional to its horizon area, then as the black hole evaporates and the horizon shrinks, the entropy decreases. Where does the information go? Either it escapes through the radiation or it is destroyed. Hawking's calculation suggested destruction. The paradox was born. Calculating black hole entropy from first principles requires counting quantum states. How many ways can a black hole with a given mass be formed? Each microscopic configuration should contribute to the entropy. In string theory, physicists have successfully counted these states for certain types of black holes, reproducing the Bekenstein-Hawking formula exactly. This was a major triumph, showing string theory can account for black hole thermodynamics. The calculation involves counting the vibrational modes of strings and branes that make up the black hole. Each mode is a quantum state sum over all possible modes, and you get the entropy. The fact that this counting matches the geometric area formula is not obvious. It suggests deep connections between quantum information, geometry, and entropy. Loop quantum gravity also reproduces Bekenstein-Hawking entropy through a different mechanism. In loop quantum gravity, area is quantized coming in discrete units. The event horizon has a finite number of area quant. Each quantum can be in a finite number of quantum states. Count all possible states of all quanta, and you recover the area proportional entropy. Again, quantum mechanics reproduces the geometric result. These successes strengthen confidence that black hole thermodynamics is real and that quantum gravity in some form correctly describes black holes. The Bekenstein-Hawking formula is not just an approximation. It is exact, emerging from the microscopic quantum structure when calculated correctly. This exactness constrains theories. Any proposed quantum gravity must reproduce this formula. Bekenstein-Hawking entropy remains one of the most important clues about quantum gravity.